journals come from?
The journals came from my office.
I see.
So your homework assignment for this week is, in addition to just doing whatever problems you want, because you're graduate students this week, is choose a journal, choose an article from the journal, and write a summary about it. And I'll send you details as to what the summary should include. If you don't like any of the journals or any of the articles here, I'm happy to provide additional ones. I'm happy to talk to you about what you should do. This is a good skill I want you to have. Read a technical paper, summarize what's going on. Also, if I ever have to write letters of recommendation for you, it's one more non-trivial data point. If you want to be paid to do this in AMS money, let me know and I will give you an AMS article to do instead of one of these. Alright, so what I want to try to do today is Fourier analysis to the uncertainty principle in one lecture, assuming no physics knowledge. So, for the most part, we will just assume that these operators correspond to the physical things that we know of as position and momentum. And if any of you are really interested, by all means talk to me, the physicists, the physics department, go to the Fountain of All Wisdom. There's lots of places that will talk about that. That's not my department as a math professor today. I am not going to prove all of the results I need from Fourier analysis. The proofs are in or are sketched in the handouts I've given you towards the end. I find that the further you go into the notes that I gave from when I was an undergraduate from the textbook we used, the harder it is to follow what is going on. And so I will try to really expand on what's going on. You will see the mistake I made in confusing Parseval and Plancherel is really not that bad. The proof of Plancherel, which is the L2 norm of F, is the same as the L2 norm of F hat, is essentially a consequence of Parseval's identity. So this is why I confused the two earlier. I am not going to worry about convergence issues. Why?
Because we're physicists?
Yes, because we're physicists today, right? We're physicists today. That's worth a huge number of eminence. Okay, if you don't want them, you can give them to Philippe. Okay? So we're going to start off by looking at a wonderful space of functions called the Schwartz space. Okay, so
is the Schwartz stronger?
yes, but you have to know how to handle it. Okay, so the nice thing about these functions is whatever decay you want, within reason, they have. So the function and all of its derivatives decay faster than any polynomial at infinity. So we say f is in the Schwartz space of R if for all m and n greater than or equal to 0, we have 1 plus the absolute value of x to the m, nth derivative of x goes to, well, we'll just do it this way, is less than infinity. So what this means is take however many derivatives you want and multiply by whatever polynomial you want. Okay, and again, why do I have 1 plus the absolute value of x? Why don't I just have the absolute value of x? Not just 0. If x is 0, then multiplying by x to the m would just make everything vanish.
Because otherwise it at the unit disk would be helping.
Yeah. If absolute value of x is less than 1, then raising x to the nth power is going to make things smaller. So this is why, to just cover myself, I always do 1 plus absolute value of x. And so if this is bounded by some number, well, if I just replace m with m plus 1, it's also bounded. So I could also say that this tends to 0 as x gets large. So same as 1 plus the absolute value of x to the m, f hat of n of x goes to 0 as the absolute value of x goes to infinity. Any convergence issues you might have vanish if you use the Schwartz space. Okay, the Schwartz space is extremely nice. To match the book's notation, I apologize. Do we really want to use y rather than c? I'll do y. It'll just not match the book, but that's fine. F hat of y is the integral from minus infinity to infinity of f of x e to the negative I x y dx. Yes?
What's an example of a Schwartz space function?
Okay. I was actually going to get to that in a little bit, but I will take that right now and I will turn it around. Give me an example of a Schwartz-based function.
0.
Okay. Give me a non-boring example of a Schwartz-based function. So it's going to be infinitely differentiable, and it's going to decay extremely fast. So exponential e to the minus x is nice, but I have issues at the origin. I could try e to the minus absolute value of x, but then I've got this kind of cusp at the origin. So what's related to e to the minus x that might be nice?
E to the minus x squared.
E to the minus x squared. So Gaussians are great examples of Schwartz functions. And in fact, I'm probably going to hold off on this until Wednesday. The Fourier transform of a Gaussian is a Gaussian. And that's a really nice property. So if you want, every time you see Schwartz space, think of a Gaussian. So not only is it integrable, but any power of it is integrable. All of its moments exist. I can integrate, x to the nth, f of x, perfectly going to be fine. The function's in L1, the function's in L2. I have wonderful decay. What are we missing here? The 2 pi. And so it's always a pain who puts the 2 pi's where. And this is going to make certain formulas very ugly, but it's going to make other formulas very nice. And so it's a question of which do you want to fix. So the first, some facts. So one is the inversion formula. Well, I'll just say if f is in the Schwartz space of R, f hat is in the Schwartz space of R. So this is really nice. The Schwartz space is mapped to itself. So if you start off with rapid decay, then your Fourier transform also has that rapid decay. What this means is I don't have to worry about imposing separate conditions so that things involving f hat also converge nicely. If f is Schwartz, f hat is Schwartz, convergence everywhere is going to be great. This is going to eliminate certain functions. So for example, one of the functions that was eliminated is we talked about this function that was getting more and more peaked over the integers. Where this was n plus 1, n plus 2. It was converging to 0 almost everywhere, but it was exploding on smaller and smaller sets. This is not going to be in the Schwartz space. Well, for those of you who do physics, you really should not be seeing something like this for the probability distribution of where something is, this strange thing going off to infinity. So this is not a bad assumption. Okay, I will try to remark when we have bad assumptions. But the Schwartz space is very good. The other thing which we're not going to really get into in this class unless you vote otherwise is if I give you a function in L1, I can approximate it with step functions, functions that are constant on intervals. I can approximate those functions with continuous functions. I can approximate those continuous functions with Schwartz functions. So what you can often do is you prove results for Schwartz functions, and then you work backwards, and you do some kind of convergence arguments to show that the same result holds for the more general L1, L2 functions. So it's not necessarily too restrictive to work with the Schwartz function. At the end of the day, if you want results about L1, L2 functions, you can get them. You just have to go through some analysis. Measure theory is not a prerequisite for this course, just real analysis. Don't worry, I haven't changed the prereqs. So we will not go through those arguments in detail, but I just want you to be aware of what needs to be done. So the first is the inversion formula. F of x is 1 over 2 pi, and I'm checking my notes just to make sure I give the correct inversion formula, because everybody does it, yes. Minus infinity to infinity, f hat of y e to the I xy dy. So what we've basically done is rather than integrating with respect to f with respect to x, we integrate f hat with respect to y. Rather than having a negative exponential, we have a positive exponential, and we have a 1 over 2 pi outside. You can now get a sense of why I don't like this normalization. You have these factors of 1 over 2 pi that you have to remember when you're doing the different integrations. Okay, the next one is we're going to define some operators. Q of f at x is going to be defined to be x times f of x. And you can ask the physicists why they spell position with Q. Does a physicist know why you spell position with Q?
P's already taken.
Yes, P is already taken for momentum.
That was wrong.
Right? We'd love to use P for position, but sadly we use P for momentum.
I thought momentum was rho.
No, P. P.
That would be the difference.
Pf of x is minus I d by dx acting on f of x. And this is momentum. Okay? So again, not my department to explain why this is position and momentum. Okay? You have plenty of people in this class who I'm sure will be happy to talk to you about this. Okay? Think of derivative of distance as speed. And momentum is related to speed. In your classical Newtonian physics, momentum is mass times velocity. So up to mass, this is essentially momentum classically. And if we have mass of 1 unit, then that's perfectly fine. Okay? So it's not so unreasonable to define this to be momentum. Now, an interesting question to ask is, what is the relationship between certain transforms of a function and the Fourier transform? How do they interact? So for instance, what is the Fourier transform of Pf? So that would be the integral from minus infinity to infinity. So we have the Fourier, so Pf is minus I f prime. E to the negative I x y dx. Right? Because by P takes my function, it takes the derivative and multiplies by minus I. Right? There is a reason why we want this minus I. How would we evaluate this integral? Integration by parts. And now you can begin to see why I want my function to be in the Schwartz space. What will the function in the Schwartz space allow me to deduce when I integrate by parts? I get rid of the boundary terms. So u would be f prime of x, no, dv is f prime of x dx, v is going to be f of x, u is minus I e to the minus I xy, du is equal to what? So when I take the derivative with respect to x, the minus I comes down. Minus I times minus I is minus 1. I get a y, so I get minus y e to the minus I xy dx. And so I get Pf hat of y. The boundary terms vanish. The negative sign takes the negative in the integration by parts and makes it a positive. I integrate minus infinity to infinity of y. I'm sorry. X e to the negative 2, I'm sorry, e to the negative I xy dx.
Where did the UV part go?
I'm sorry?
The UV.
The UV cancels because f is Schwartz. And this is exactly why I'm assuming f is Schwartz, so I don't have any boundary. Is this integral easy or hard to do? Easy. Why is this integral easy? Y times f hat of x. Right? I'm integrating with respect to x. I can pull the y outside, and that's the definition of f hat. So I get it's just y f hat of y. So what Fourier analysis is telling us is the Fourier transform of the derivative is basically the multiple, is basically multiplication. Which would you rather do? Take derivatives or multiply? Multiply. So what often happens, and there's a big problem, big industry in solving partial differential equations by using Fourier analysis, by taking Fourier transforms. You convert derivatives to multiples. Then you solve, and then somehow you invert. And the somehow you invert is the difficult step. but there's a lot of differential equations that can be very easily solved by using these techniques. And you're supposed to be choosing the problems you want to look at this week. There's a good problem in the book about, I think, the heat equation or the wave equation, and solving that using Fourier analysis. Fourier transforms convert differentiation to multiplication, and then you can see, well, what if I took the Fourier transform of x times f of x? What would that be? And you could see what that would become on the other side. So I don't think I need that, so I'm not going to really bother going through it. This is the one I need. The Fourier transform of the derivative is basically the multiple. Now, I have been potentially unfair to the people who favor this convention by saying how I dislike it so much and how I don't like the 1 over 2 pi I have over there. Can somebody say something nice about this convention? So if I put in 2 pi's in the exponential, I wouldn't have the 2 pi there, but I'd have a 2 pi here, I'd have a 2 pi here, and I'd have a 2 pi over here. So then all of a sudden, when I take a look at what is the Fourier transform of the derivative, now all of a sudden 2 pi's would come in. So no matter what you do, somewhere you have to pay the price. The question is just, where do you want to have that happening? Okay. So we have the Fourier transform of the derivative. Okay, the next property I want is Plancherel. And so I am not going to prove Plancherel. There is a sketch of the proof of this in the notes. It basically comes from looking at finite intervals from minus L to L, using Fourier series, and then taking the limit as L goes to infinity, and using possible. Right? So Plancherel, I'm going to introduce some notation. This is going to be the integral from minus infinity to infinity of f of x squared dx. So this is called the L2 norm. And so the actual L2 norm would be the square root of this. So by putting in the square over here, I'm just avoiding the square roots. The L1 norm would be integrating this to the first power. The L3 norm would be integrating this to the third power. So f, the L2 norm of f is 1 over 2 pi the L2 norm of f half. I just want to make sure that there's no square roots, that everything is fine. Yes. Okay. For those of you who do physics, is this the notation you use for the Fourier transform? Okay, you have the 2 pi's. I like the 2. So, see, that's the thing. Is
Depends on the class.
It depends on the class. And so over here, you don't quite have a unitary operator. Things have been changed a little bit between f and f hat. Sometimes people actually try to appease everybody and split the difference and have square roots of 2 pi. So in some sense, basically, everybody's a little bit happy and everybody's a little bit upset. So there's basically 3 major schools of normalization. Okay, so what this is saying is this is very similar to possible. Possible was the sum of f hat of n squared equal the integral from 0 to 1 of f of x squared dx. This is the L2 norm of f. This is the generalization. And the sum of the squares of f hat become the L2 norm of f hat. And the 1 over 2 pi is just because of our normalization conventions. Okay. Any questions on what we've done so far? So the next thing is basic probability. Right? So if you've taken a probability class with me, then fortunately you have seen all this before. There is a non-trivial intersection between people who have taken probability with me and people who are physics majors. If you find that non-trivial intersection, you can have all the answers, all your questions answered by one person. Okay? So what concepts do I need? I need the fact that f is a probability density. Actually, I'll use little p. Means p of x is greater than or equal to 0. The integral from minus infinity to infinity of p of x dx equals 1. And then the probability a less than equal to my random variable x less than equal to b is the integral from a to b of p of x dx. So I have some random variable with density p. If I want to know what's the probability I land between 3 and 5, I just integrate my function from 3 to 5. If I want to know what's the probability its value is greater than 1 in absolute value, I would integrate from minus infinity to minus 1, and then 1 to positive infinity. This is, in fact, one of the main reasons we care about integration. Integration allows us to calculate probabilities. In physics, their probability function p is actually the magnitude squared of the wave function. So for the physicists, physics, I think you would write it like that. Or for us, we would write it like this. Okay. So it's just what are we using for our density function? In physics, they take the magnitude squared of the wave function. And that's what happens to be the correct definition to use. Professor Woodis is a great person to talk to about complex numbers in the world. We can't measure anything directly with a square root of minus 1 in it. Everything we measure has to be real value. We can use the imaginary numbers to try to simplify the algebra, to try to generate the theory, but at the end of the day, we can only measure and talk about real valued objects. And so magnitude squared, that's a really good thing to do with an emphasis on the real, because magnitude squared will be real valued. Okay, there are two more basic things we need from probability. Any thoughts on what they might be? In a pre-med calculus class where the students are highly competitive on the grades, they would know this immediately.
Distribution.
Okay.
Deviation.
Standard deviation
Oh.
and mean. I was once visiting a friend at Harvard who was pre-med, and the physics professor posted, everybody's scores, with their student ID, so you know who got what, and listed the mean, the variance, the third moment, and the fourth moment of the class, so that you could really place yourself relative to everyone else.
I think maybe the better policy is not to tell anyone the mean or median. But I've had professors who refuse to tell me, and it reduces the focus on how well you are relative to the class.
Right. No, it's a really interesting question as to what information do you want to provide. I go to the ridiculous extreme, I think, of telling you how everybody does on average on each question. With here's the mean value, median value, standard deviation, and I want you to get some sense of which problems are hard, which problems are not. I never grade people on a relative scale in my classes. It's always on an absolute scale. So you're just competing with yourself. Okay, there's a good Dr. Seuss book on stuff like this. All right, so we need two more concepts. We need the mean, and we'll often write this as the expected value of my random variable x is the integral from minus infinity to infinity of x p of x dx. So think of this as the average value. And the next is the variance. It's going to be, and we often denote the mean by the letter mu. This is at least a good definition. Mu is the Greek letter for yeah. If I'm telling you it's a good, right? So mu is coming from mean. So the expected value of x minus mu squared. So the reason this is a natural quantity to study is I'm looking at my fluctuations about the average value. The only thing I know is the average value of my distribution is mu. Let's see how likely it is to be so far away from it. So this gives me a sense of scale. And this would be the integral from minus infinity to infinity of x minus mu squared p of x dx. And we write this as sigma squared. It turns out, if you do some algebra, this is the same as the expected value of x squared minus the expected value of x squared. And it's reasonable that the expected value and squaring operators do not commute. So this is going to be a big issue today, lack of commutativity. One of the reasons, so imagine expected values and squares commuted. Then the variance would be 0, and the variance of every quantity would be 0, so everything would be completely localized and there would never be any change. I'm sorry?
Lovely.
Yes, you wouldn't even be able to say lovely unless all you just did is lovely, 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 lovely. Right? That's all you would be able to do.
Oh, right. I can deviate.
Right, no deviates.
Oh, right.
No deviates. Okay? So how would we prove this? If we just expand out x minus mu squared, so proof. X minus mu squared is x squared minus 2x mu plus mu squared. And then when I take the expected value, when I have x squared times p of x, that's going to be the expected value of x squared. So I define just the expected value of x here. If I had an x squared, I would put a squared here. If I had a cube, I would put a cube there. So when I do the expected value of x squared minus 2x mu plus mu squared, since integration is linear, this would become the expected value of x squared minus 2 mu expected value of x plus mu squared, the expected value of 1. And the expected value of x is mu, so I get a minus 2 mu squared plus a mu squared, that's a minus mu squared. So this would be the quick proof that the variance is the expected value of x squared minus the square of the expected value of x. The variance is the wrong quantity to study. If I want to ask, how tall is the average American? If I said the answer is, I know I'm doing a physics lecture and I should not use feet. Alright, 1.8 meters, is that reasonable? Yeah. So the average American can say, 1.8, 1.9 meters, plus or minus, 0.4 meters squared. Okay. You would not give fluctuations in people's height in meters squared. Meters squared is an area. You would give fluctuations in meters. And that's why the standard deviation is the more significant one. So standard deviation, sigma, is what? Yeah. So the notation of the variance is highly suggestive on what you want to do. Right? We're defining the variance as sigma squared. When you see that as a definition, you should be expecting at some point I'm going to be taking a square root. Okay. So of course there's a lot more to do in probability than just that, but this is what we need for today. Okay, moving on. Alright, I think we're now ready to do the strange operators. We've got inversion, Plancherel. Oh no, we have one more thing to do first. Cauchy-Schwarz, right? We haven't seen Cauchy in a while.
The two great powers.
Now, for extra credit, who's the third person whose name is sometimes attached?
Leo.
No, but not bad.
Weierstrass.
Nope.
Marcel.
I'm sorry?
Marcel.
Nope.
The other Plancherel.
Nope. So it begins with a B. I think it's a Russian. They sometimes add his name as well. How many of you have seen the Cauchy-Schwarz inequality? Brunievich, I think, something like that.
Close.
How many of you have seen the Cauchy-Schwarz inequality? How many of you can prove the Cauchy-Schwarz inequality? Exactly. That's just a random cost. What? If you're going to call yourself a math major, there's a couple things you have to be able to do on the fly. Proof of Pythagoras, absolutely. Proof of Cauchy-Schwarz, without a doubt. Unless you want to be like algebra 8, okay? But if you want to consider yourself an analyst, you've got to be able to prove Cauchy-Schwarz. All right. I'm going to use the most useful inequality in mathematics to prove this inequality. What inequality is that? Nope. Yes. If I take a real number and square it, it's greater than or equal to 0. So this says the integral of the absolute value of f of x, g of x, dx squared minus infinity to infinity is less than or equal to the integral of f squared dx minus infinity to infinity integral minus infinity to infinity g of x squared dx. I guess I should put an x over here. if you think about units, if F and G are both in meters, this would be meters squared to the fourth, meter squared, good. Everything would work out perfectly.
QED.
I'm sorry?
QED.
QED. So let's prove the Cauchy-Schwarz inequality. Okay? I'm going to make some simplifications. My favorite logarithm, the W log. Right? What is W log?
With loss of
Without what?
With loss of general.
With loss of generality. No. I had a friend in college who was foreign who accidentally said without loss of generosity. Without loss of generality.
Very different term.
We can assume F and G are non-negative. Why can we assume F and G are non-negative?
Because square. Absolute value.
Absolute values. You've got to be careful. It's not the same as squaring because they could be complex valued.
Okay.
But I'm squaring everything, so I might as well assume F and G are non-negative. So what we're going to do is a tweak on the method of divine inspiration. I'm going to look at the integral of F minus lambda G squared dx. And lambda, I will assume, is real valued. What can you tell me about this integral? Non-negative, right? I'm integrating something that's non-negative, it's non-negative. When I expand this out, I'll get the integral of F squared minus 2 lambda integral of Fg plus lambda squared integral of G squared. Okay? I'm just expanding everything out. And I'm going to be lazy today and not keep writing minus infinity to infinity and dx's and whatnot. Alright, so if I regroup things, I get 2 lambda integral of Fg is less than or equal to the integral of F squared plus lambda squared integral of G squared. This is true for all values of lambda. So I can try to figure out what lambda maybe in some sense minimizes things, maximizes things. I could try to do something like that. Even when do I get an equality? I'm going to use the method of divine inspiration. Okay, and just say, why don't I look at the following special value of lambda? And so I'm going to take lambda to be the integral of F squared divided by the integral of G squared. But I claim that this is a natural choice. Well, actually, if I square it, I claim it's a natural choice. The other one was a horrible choice. If I square it, it's a great choice. If lambda squared is integral of F squared over integral of G squared, oh look, the integral of G squareds cancel, and I get twice the integral of F squared. I have a 2 over here, the 2's cancel. And so when I substitute, when the dust settles, the 2's cancel, I have lambda, so I'm going to have a square root of the integral of F squared over the integral of G squared times the integral of Fg is less equal to the integral of F squared. And now, if I just multiply through by the integral of G squared over the integral of F squared, we're done. Therefore, the integral of Fg is less equal to the integral of F squared, integral of G squared. For an M&M, where's the mistake in the proof? Yes?
What if the integral of G squared is 0?
Excellent. Do you have a preference for color?
Orange, please.
Nice.
No, I'm treating you guys like my children. My children definitely have preferences, and they will tell me, so I'll ask you later why orange. But is it tigers, actually? Okay.
Makes sense.
Makes sense. So that if it gets caught on your sneaker. Okay. What would happen if the integral of G squared was 0? I can't do this. Well, if the integral of G squared is 0, the only way that can happen is if G is identically 0. This is not a hard inequality to prove if the integral of G is 0. There's one other issue I could have.
Didn't we also say that G is greater than or equal to 0? Or, oh, we say greater than equal to 0.
But G could be identically 0, right? So, I'm only like 98% physicist today.
Yeah.
I still care a little bit about stuff like this. What other issue do we have? So I have one issue in addition to what if the integral of g squared is 0? What else could go wrong?
So,
What's the other dangerous operation in mathematics?
Well, I'm just curious, how did you get the integral of fg equals, is also equal to the integral of f squared g squared?
Over here, I just multiply by the square root of integral of g squared.
Well, wouldn't you have to
Oh,
square
sorry. And then,
one of the sides?
sorry,
has to
yes,
be
you're right. One of the sides has to be squared.
Yeah.
You're absolutely correct. Yes, I forgot to square. So one of the dangers in mathematics is division by 0. What's the other thing to worry about?
We have to worry about one of the functions maybe blowing up.
So what if one of the functions integrated to infinity? Well, if both of them integrate to infinity, no problem. If one integrates to infinity and one integrates to something finite, no problem. Right? So, without loss of generality, all integrals are finite, non-zero. Okay? So technically you do have to worry about those cases. But if both of these integrate to infinity, I'm really not that worried. Okay, so this is the Cauchy-Schwarz inequality. It allows me to bound the integral of fg in terms of the integral of f, the integral of g. If you want to think about it in terms of inner product spaces or dot products, if f and g are in L2, then f times g is in L1. And in some sense, I can define a dot product between two functions f and g. I don't really have time to go into all of the details of this, but just to give you some sense of the general theory. What's nice is you don't have to raise your hand if you don't care about physics. Even if you do not care about physics, there's a lot of really good things in mathematics that you're seeing today. And that's one of the reasons why I still was willing to do this lecture, even if you don't care about physics. Okay, so we've got Cauchy-Schwarz. So the next thing we need, what are we on now? What was the last thing I labeled? Was it 4 or 3?
4.
Okay, did I label Cauchy-Schwarz?
No.
Alright, so Cauchy-Schwarz should be 4.
That'll be 5.
5. Okay, so 6 QP. Let's see, I want to make sure I do it in the right order. No, they want to do PQ. PQ minus QP is minus I times I. So what this is a statement of operators. The capital I operator just means take your function and return it. It's a very easy function to understand. P means take the derivative and multiply by minus I. So P of f is minus I f prime of x. Q of f is x f of x.
What was I again?
I is the square root of minus 1. Oh, big I is just the identity.
Oh, okay.
So I f of x is just f of x. It's the do nothing.
Okay.
So now, if I look at PQ minus QP acting on f. So for those of you who haven't done quantum mechanics, if I take a particle's position and multiply it by its momentum, is that the same as taking its momentum and multiplying by its position?
No.
That's the correct answer, but what are you supposed to say?
No. Definitive.
Should the order of multiplication matter? Right? Position times momentum should be the same as momentum times position. You know, they should commute. And physics and quantum mechanics, they don't. Finding something's position and then finding its momentum is not the same as finding its momentum and then finding its position. This is the tip of the iceberg in terms of what they do. Okay?
Those people.
Those people. But it leads to a lot of products you use in everyday life. And so we can't prove quantum mechanics is right, but it does lead to a lot of technology that works very, very well. Is it surprising that PQ minus QP is not the zero operator? So again, it would be the zero operator if you commuted. Why is it not surprising? I'm sorry?
You have a product rule.
Have a product what?
A product rule? Be a little bit more specific.
PQ would be like when you work out the math, it doesn't work out.
Yes, when you do the math, it doesn't work out. But why are we not surprised that the math doesn't work out? What's going on?
We're taking a derivative.
We're taking a derivative. So when you take derivatives, you don't expect order to be immaterial. And there your product rule will come into play. So when we look and see what happens, this is P of QF of X minus Q of P of X at X. Alright, so the first thing here is I change my function, and my function is now X times F of X. And now when I apply P, I apply the operator minus I d by dx. So I get minus I, the derivative hits x, so I get f of x, minus I x f prime of x. Over here, I first get a minus I f prime of x, and then the q multiplies this by x. The minus and the minus become a plus, so I get plus I x f prime of x. So when I just figure out what this operator does to an arbitrary function f, I get minus I f of x minus I x f prime plus I x f prime. Alright, the last two cancel, and we get minus I f of x, which I can write as minus I, the identity operator, acting on f. And because this is true for any function f, we deduce that pq minus qp is the same as this operator. Alright, it's going to be close. So, in order to make sure I finish this lecture by 11:50, I don't want anybody to be observing the time, only observe my position or something like that. Here. We're almost there. Alright, so now, 7. The uncertainty principle. So, I'm going to define the mean of the quantity I care about to be the integral from minus infinity to infinity of x, f of x squared dx. Think of f as your wave function. So the square of it, the modulus squared, is going to be your probability distribution. And I'm calculating the mean of the probability distribution. I'm sorry, that's going to be mu. That'll be mu. And sigma squared will be the integral from minus infinity to infinity of x minus mu squared f of x squared dx. I can do the same thing on the Fourier transform side. Mu hat will be the integral from minus infinity to infinity of y f hat of y squared dy. Sigma hat squared would be the integral from minus infinity to infinity of y minus mu hat squared f hat of y squared dy. And then the claim is sigma squared, sigma hat squared is greater than or equal to 1. Maybe up to or 2 pi. I think it's fine the way I have it, but just in case I will cover myself. Oh, forgot to turn the camera. So I will cover myself and put in a 2 pi. So again, f hat squared is my probability wave function. Modulus squared, it's going to give me my probability density. This will be my mean, is just going to integrate f times that, variance x minus mu squared times that. I can also use the formula that the variance is the expected value of x squared minus the expected value of x quantity squared. I can do the same thing for f hat and get a mu hat, sigma hat. And then the Heisenberg Uncertainty Principle is that the product of this is greater than or equal to 1. So what does this mean? Well, the smaller sigma squared is, the more mass is concentrated near mu. The more I understand what my f looks like. Well, if that's getting smaller, then sigma hat squared has to be getting larger. So what that means is, as you localize a function f, your information about its Fourier transform is becoming less and less precise. It's able to live in greater and greater regions. Conversely, if you localize a function's Fourier transform, you have less and less information about the behavior of the function itself. So this is really the mathematics of the Heisenberg Uncertainty Principle. The physics is that somehow this is actually related to position and momentum. Okay? So all the stuff I'm erasing right now with the F's and the P's and the Q's, all this stuff is just saying that in physics, this has meaning. Okay? The meaning is the uncertainty principle. For us as mathematicians, we don't really care or don't necessarily have to care about that. This is just a statement about a function and its Fourier transform. And so what I'll do is, I think in the interest of time, I will assume the means are 0. Just to make things nice, I've got things normalized. You can go through these arguments and do it more generally, but to save time, mu equals mu hat equals 0. You can see the notes for the general case. You just tweak this operator to include p minus its mean, q minus its mean. Okay. Without loss of generality, assume the L2 norm of f equals 1. You know, it's a probability distribution, so it should integrate to 1. Alright, so I have 1 is the L2 norm of f. And this is the same. So how do I do this? 200. Alright. It's I times PQ minus QP acting on F. So if you think back, this operator over here, this is the same as minus I times I. So if I put in this extra I over here, this is the same as the identity. Is this I going to really change values? No. Everything's still going to be of size 1. Okay? So now, I can start playing my games. I'm taking inner products, I'm taking dot products. Okay? This means take the integral of PQ minus QPF times F bar. And so we need to start playing some games. And so after some algebra, you'll see QF of F is the same as F Q of F. And PF of F is the same as F P of F. And in fact, this is one of the reasons why we've introduced a minus I in the definition of P. So just go through and do the algebra. This is the integral of Q of F of X times F of X bar dx. And this is the integral of F of X, Q of X, QF of X bar dx. Okay? So after we do some algebra, we get 1 is equal to I. So we've got PQFF minus I times QPFF. Moving operators around, this is QFPF. I can move the P over by the stuff above. Minus I PFQF. Notice these things are just in opposite order. That means they're complex conjugates of each other. Okay? This one had an I, this has a minus I, so when I take the complex conjugate of this, I should get something like twice the imaginary part of either PFQF, or maybe it's in the other way around. I don't care. It's imaginary, it's real. The lecture is ending. I don't have time to figure out which one it is. We have like 1 minute left. It's either the real or the imaginary part. It's either in the order PFQF or QFPF. You just have to figure out which one it is. What can we use to estimate this integral?
Cauchy-Schwarz.
Cauchy-Schwarz. So putting in absolute value is 1. The absolute value of 1, we're not going to draw absolute values around 1, that would be a nightmare to read, is less than equal to 2 times the absolute value of the integral of, PF, QF, PF of x, QF of x, bar. Or I can bring the absolute values inside. I can square everything. And so if I square everything, this will be less than equal to the integral of P of f squared, the integral of Q of f squared. The integral of P of f squared, this is the same as the integral of P of f hat squared, integral of Q of f squared. Why is this the same as P of f hat? And I might be off by a factor of 2 pi, probably a 1 over 2 pi. Why is that the case? Plancho L, right? The L2 norm of a function is the same as the L2 norm of its Fourier transform. So I'm not worrying about factors of 2 pi and whatnot. I just want to get this some constant such as the product of the variances. This is now, I'm assuming I have mean 0. This is the variance in position. This is y squared f hat, because the Fourier transform converts differentiation to multiplication. This is the variance in f hat. So this piece becomes essentially the variance of f hat, a variance of momentum, and this becomes the variance of position. Okay? And this is essentially the proof of the uncertainty principle. This is where it comes from. Okay? So at the end of the day, this is just now equal to y, and I have like a y squared, absolute value of f squared. That's how I'm defining variance. That's the variance of the momentum. The other one is x squared times the absolute value of f squared. That's the position. And there's the Heisenberg Uncertainty Principle. So you just now collect the factors of 2 and pi and everything like that. And there you go. You cannot simultaneously localize position and momentum. Right? This is probably complete information over